So we talked about how the models use technological promises from uh, carbon capture and sequestration, bioenergy, and so on, which are not yet ready for prime time in terms of scalability and other issues, but we say models may be relying too much on those technological promises to offer pathways to meeting global warming targets, and of course countries can rely on them to submit their nationally determined contributions, and IPCC models look at the pathways and tell you about how extremes will change, how precipitation distribution will change, crop yields will change, health impacts, and so on and so forth. And yet we have to prepare for the possibility that we will hit net zero at some point this century, and then the global warming will peak, and then there will be a cooling. We may even hit some negative emission periods where we are drawing down much more greenhouse gases than the amount that we are emitting. So the question is, how do we prepare for such a post-net zero world? So the warming scenarios and the associated impacts in the physical, biological, ecosystem world and so on may be being looked at the models, but there are very few models which have looked at what the cooling rate would mean for distribution of precipitation, again, equity to make sure poor countries are not harmed again, like they are being harmed during the warming, not entirely being responsible for the emissions that are causing the global warming and so on. So all these issues have to be considered as well. So even though we have lots of uncertainties about hitting net zero, we must also at the same time think about what happens once we do achieve this goal, because the idea is that we have to achieve this goal. There's no choice in this matter, right? So this article writes an opinion about this with various issues that I'm going to include here in this podcast. Current greenhouse gas emissions will continue to affect the climate even after we reach net zero emissions. So cumulative carbon has a long residence time. It'll take time to equilibrate. So even when we hit net zero, the impacts will continue for some time, especially the warming, the glacier melt, sea level rise, and so on. We must understand how and prepare for a cooling planet. Okay, so this paper then looks at a framework for delivering climate projections consistent with the Paris Agreement. So remember, Paris Agreement is totally focused on global warming targets, 2 degrees C warming by 2100 with a probability of, let's say, 67%, and try to stay as much as possible below 1.5 degree pathway by 2100, again with a 67% probability. Then there is retrofitting of the pathways that also make sure that we are sustainable along the way, and that's projected or mapped onto the Sustainable Development Goals, which try to protect the poor people, the women, the children, and so on, to make sure the solutions are mitigation pathways are equitable and just, and so on. Keeping that in mind, this is looking at A to D instead of the traditional method of model intercomparison project, in which prescribed radiative forcings like these radiative forcings, so business as usual or high emission scenario will take you up here 8.5 watts per meter squared by 2100 in terms of the net energy imbalance, and the low emission pathway, let's say consistent with the 1.5 degree pathway. Then the models are used to look at constrained radiative forcing causing the spread of warming in the global mean surface temperature by 2100, but going forward all the way to 25 100, so that even if we meet our goal by 2100 of 2 degrees C, the warming will not stop because of this committed warming or the impact of cumulative CO2 that will not be totally gone. Okay, so we are talking about net zero emissions versus cumulative carbon since industrial revolution. You have to make sure you understand the difference there. Okay, in B we propose that modeling, so that's B in terms of what warming's result. So we propose that modeling centers adopt differing radiative pathways for each model. So instead of these pathways, you look at different pathways. So the low emission pathway will continue for some time to increase, which is different than here, and then continuously decrease, and then the intermediate pathways all the way to the business as usual. So this would then spread of radiative forcing to constrain global mean surface temperature will give you different pathways to the warming. So here you are going to hit, the scales here are cut off, so you can see that we're going up to 3000 here, so just be careful. So we'll hit 1.5 degrees C and keep it there for a long time if we keep on reducing the radiative forcing, unlike here focusing only on 2100, and similarly for other radiative forcings that keep dropping, to keep the global warming targets at that level for a long time. So regional climate evolves after global temperature stabilization, where you are stabilizing temperature and not just emissions. Okay. So in C and D, let's see here, differing radiative forcing pathways for each model to enable stabilized climate projections at 1.5, 2, 3, and 4 degrees C warming. In C and D, the gray bars indicate when carbon dioxide emissions are set to zero to achieve the desired global warming levels, which will vary across the ensemble of models. So you choose different potential timelines where net zero will be met. Models that warm faster will turn off the carbon dioxide emissions earlier than models that warm more slowly. So now we already have lots of models participating in assessment reports under IPCC, and each model runs multiple scenarios. Some have high climate sensitivity, so warm faster and more by 2100, let's say, than some other models. So this accounts for the distribution of models as well. GMST, the global mean surface temperature, is a schematic illustrative purposes only. But coming back to what we mean by cumulative carbon dioxide emissions determining the warming, we've talked about this on several occasions in other podcasts and other courses. So looking at cumulative carbon emissions in trillion tons of carbon since Industrial Revolution, we now know that there is a fairly linear relationship between cumulative carbon emissions and temperature change. So even there you can see that the models have different sensitivities. This is what we meant in the previous plot here about models that have high sensitivity and the models that have low sensitivity. So here is the HAD-CM3LC from the UK, which shows much more warming for the same level of cumulative carbon than the green one here, which is the Max Planck, I think, or maybe it's CSM1. These colors are too close to each other, but the point is that there is a range of warming indicated by the models for the same cumulative carbon levels. To keep this in mind, there is also a carbon climate response function defined in this paper, which I should have, it's the same paper, this one. Okay, so this shows that CO2 emissions increase CO2 concentrations in the atmosphere, which is happening now. We have repeatedly said that CO2 is increasing at about 4 ppm, now even more than 4 ppm per year, which is driving global warming that we keep talking about, year-to-year anomalies and decadal warmings. Each decade is now warmer than the previous decade, and so on. So that depends on the carbon sensitivity, and we have defined things like equilibrium climate sensitivity, where we ramp up the CO2 levels to twice some baseline and then keep it there, and see how warming occurs during the transient period and by the time you reach equilibrium. But there is also an climate sensitivity going from level of CO2 concentration to climate change. So the carbon sensitivity determines how CO2 emissions determine CO2 concentration, and climate sensitivity determines how CO2 concentrations determine climate change. And then there is a climate carbon feedback in the middle. But when we say cumulative CO2 emissions, we go from CO2 emissions to climate change, looking at cumulative change, and there is a way to define a sensitivity there, CCR, which is looked at degree centigrade per trillion ton of carbon, and these are estimated from observations by this paper, which show that the best estimate is not constant. It varies, as you can expect, because human activities are going on during this observation period as well. And there is the 95th percentile confidence limit and the 5th percentile confidence limit. So CCR here was estimated for each decade of the 20th century after 1910 by scaling an observationally constrained estimate of greenhouse gas attributable warming relative to 1900 to 09 as the baseline, by the ratio of CO2 forcing to total greenhouse gas forcing. So you have to account for other greenhouse gases as well that have accumulated, and dividing by cumulative anthropogenic carbon emissions over the same period. So delta T divided by cumulative emissions. This observationally constrained estimate of CCR is both stable in time and consistent with the estimate derived from models. Well, stable in time in the sense it's not wildly changing over this period. But the main question we have to ask is whether this CCR will be the same in the post net zero world, where we may get into cooling. So what happens to cooling and that sensitivity, and how that will translate to climate impacts, especially in terms of rainfall changes and crop losses. This will be very critical, especially for the global south, who may again be bystanders, maybe not so innocent by 2100 or 2050, because they are continuing to grow in their economies and emitting more and more as well. But historically, so far, they have not been the big players. Okay? So what are the factors that will determine climate behavior after net zero? Keeping in mind that the cooling rates and the way in which we reach net zero and the associated global warming target, for example, will we hit 1.5 and exceed and then come back, or we will manage to stay under 1.5 all the way? We will hit 2 degrees C and hit some other peak before coming back, and how people would have adjusted to the excess warming in the meantime, how agriculture would have expanded in the meantime, may all begin to play into what people want in terms of cooling. For example, if warming above 2 degrees C or 1.5 degrees C led to some very nice weather in some places, and agriculture improved, or their tourism improved, or their lives improved in other ways, then would they want any cooling to happen? Probably not, right? So all these things will matter when we go into the post-net zero world. So let's read what the paper offers. There are many unknown characteristics of a cooling planet. The following are the major factors that will determine the nature of a post-net zero emissions climate. Obviously, this is not an exhaustive list. I will just read these even if it takes a couple of minutes. The level of peak warming. The starting point for a future with net negative greenhouse gas emissions could come after peak global warming of well below 2 degrees C above pre-industrial levels. So the target so far is that we need to stay well below 2 degrees C to avoid dangerous climate change, right? If we do cross it above pre-industrial levels in line with the Paris Agreement, or after we have experienced more than 3 degrees centigrade global warming, or somewhere between 2 and 3 degrees C, the peak warming will affect how a cooling climate behaves. So there is a hysteresis in the climate system. The warming pathways, and the cooling pathways will not be the same in terms of how the ecosystems respond, how ocean responds, how atmosphere responds, how crops respond, how the entire Earth system behaves along the way, right, in the transient response. So we have to keep that in mind. Particularly if any tipping points that cause irreversible changes to Earth's system, such as melting of the West Antarctic ice sheet, are breached. So while we go to this target before hitting net zero, if some tipping points have been reached, like the Arctic ice loss, what does that mean? We don't necessarily recover them in the cooling period, right? Even if they disappeared at 2 degrees C warming, when we cool back down to 2 degrees C, we're not going to recover the West Antarctic ice sheet for sure. They take millions of or 100,000 years to build, for example. Global mean sea level rise is strongly related to peak global warming and will continue beyond net zero regardless of the level reached. But its adverse impacts will be greater in a cooling climate after 4 degrees C warming as compared to 2 degrees C peak warming. So there is non-linearity in the impacts as well. Other effects of peak global warming are currently less well understood. These are again based on model projections, but nonetheless they are useful guidelines. The rate of global cooling will matter as well. Magnitude of global net negative greenhouse gas emissions will determine how quickly the planet cools, discounting short-term cooling effects such as those due to explosive volcanic eruptions. The effects of different rates of global cooling on Earth systems, including the biosphere, are unknown and are likely related to the preceding peak global warming level. So again, there is this non-linearity, asymmetry, hysteresis, whatever you want to call it. Economic and social costs of carbon uptake and non-CO2 mitigation to achieve global cooling may limit the rate of cooling that is pursued. So if we have hit net zero and then want to keep drawing down CO2, there will be carbon cost involved, social cost of carbon involved. Nothing is free. So how people have gotten used to the warming period and the warm temperatures and how much they want to keep paying for the future generations will play a role in deciding these things. A target for stabilized global mean surface temperature after cooling will play a role. From a geologic perspective, a justifiable aim for a future climate is one akin to pre-industrial conditions. With a response time of many centuries, the deep ocean is slowly being pulled away from its pre-industrial state. Warming has penetrated quite deep, and this will continue as long as greenhouse gas concentrations in the atmosphere remain higher than that of the Holocene. So let's say 280 ppm pre-industrial level. As long as we remain above this by some amount, the ocean will keep on doing its carbon cycle, solubility pump, biological pump, and CO2 will keep increasing in the deeper ocean as well. Right, and this will continue as long as greenhouse gas concentrations in the atmosphere remain higher than that of the Holocene. Meanwhile, human infrastructure and trade networks will have experienced some degree of acclimatization to an anthropogenically warmed climate by the time peak warming has passed. So we are already getting used to warming. It may well be that most suitable target global temperature will depend on whether the priority is to protect the world's people or to limit the long-term damage of human activities on ecosystems, the cryosphere, and other Earth systems or Earth system components that determine Earth's suitability for human civilization. So what will be our holistic goal? Will we want to protect as many species as possible or just focus on us? Those kind of questions can matter. These priorities will not be mutually exclusive, but currently we do not understand their relationships to each other. There is a major research deficiency that limits even a basic understanding of the impacts of different temperature targets after global cooling. So we have thought a lot about 2 degrees C warming, 1.5 degrees C warming, but in the cooling phase we haven't thought much about that. This is not an exhaustive list, and other factors such as methods for carbon uptake used to achieve net negative greenhouse gas emissions and the evolution of carbon sources and sinks will also affect how climate evolves beyond the point of net zero. I have one more figure which I think I have forgotten here, so I will include that and continue this in a second. Sorry about that. So this figure again from the same paper that appeared just now in August 2022 looks at the factors that will influence the nature of a post net zero climate. Okay, so we are looking at the warming we have already accomplished, and then we have to see where peak warming, the maximum level of global warming, and when it will occur. So we have broken the time here and made it kind of qualitative here because we don't know where this will happen. So there is a range of things and range of time scales and levels. The rate of cooling then has to be considered. So the speed of global cooling due to different net negative greenhouse gas emission pathways are shown here, and target global temperature where we want to stabilize a climate. Okay, so if we have a peak warming of 3 degrees C with a fast decline to early 21st century and then stabilized here, so you will end up with a range of temperatures as well. So this is the peak warming of less than 2 degrees C and less than 1.5 degrees C with respect to the pre-industrial level. So what are the factors? Peak global warming rate of cooling and target global temperatures will all determine how the Earth's climate behaves after net zero emissions are achieved. The global mean surface temperature series from Berkeley Earth is shown in black here, relative to 1850 to 1900 baseline, which you have looked at several times, and we see the accelerated warming in the recent decades. 3 illustrative scenarios that would result in different short-term and long-term climate changes are shown in red, orange, and blue. Gray shading indicates the timing, indicates the global global temperature space that could be occupied by post net zero simulations. Simulations should extend beyond the time of global temperature targets to also examine stabilization effects. So to keep it here, we have to continue the drawdown and emissions controls, whether it will be net zero, net negative, whether our total emissions will also go down so that net drawdown also goes down, and what the associated temperature and precipitation patterns are. Because remember, we are talking about global mean surface temperature, doesn't tell you what will happen in your backyard, and that's what will determine what adaptation you will need or what impacts you will suffer in terms of food, water, energy, health, transportation, and so on and so forth. Okay, so that's the point, that we have to prepare ourselves for a post net zero world despite the uncertainties of when and how we will get there. Okay.